Thank you. And thanks to the organizers for inviting me. Is the mic good? Okay. So today I'll be talking about approximation schemes for revenue maximization via symmetries. This is joint work with Pravesh Kotari, Ariel Schwartzman, who's right there, Sahil Singla, and my advisor Matt Weinberg. And Pravesh is in Carnegie Mellon now. Okay. So this is actually from the paper titled with this long title, but let's get to these words later. So the main high-level goal of this line of work is to maximize revenue. And in our setting, we have a seller who wants to sell some items, but he does not have any intrinsic value for the items and just wants to extract as much money as possible from the buyer. And there is one single buyer. And the seller does not know the exact value of the buyer, but knows the population from which the buyer arrives. Okay. And so we all know the seminal work by Meyerson for the single item setting, just to make sure everybody's on the same page. So here we get a distribution F as input, and we want to output a truthful mechanism M. And by mechanism, I mean that for any given value, the mechanism has to output an allocation and price pair. And the allocation can be a randomized lottery. And the objective is to maximize the expected revenue. So maximize the price paid by the buyer. And Meyerson resolved this very nicely with a simple deterministic mechanism of a take it or leave it price. And can we say the same about multiple items? What happens here? We will stick to independent items. The whole talk is about independent items because, as you saw, correlated stuff is hard. And now we have a seller with multiple items and a buyer whose value for the items, why is this different? Okay, the value for the items are drawn independently from different marginals. They don't have to be identical. And the the buyer's value is from the product distribution. And the way the valuation works for multiple items can be defined by different functions. And people have studied many different valuations, and unit demand and additive are one of the more popular ones. I have information about additive because it's been studied a lot on the slides, but I won't be talking about them today. We consider a unit demand buyer, so the buyer's valuation for a set of items is going to be the max valuation of each of the items. So the buyer does not have the time to play all three sports. She only wants to buy one of the balls. So even if you give her multiple items, she only values one single object in that set. Okay. So we will only consider unit demand buyers. I want to now formalize this problem, and I'm going to use computation as my lens. I'm a computer scientist after all. So the input is going to be n independent distributions. The output is going to be a truthful mechanism. Again, the allocation can be a randomized allocation. And the objective is to maximize revenue. Okay? And the question we want to answer is, can we find an optimal truthful mechanism in time polynomial in n? Let's try it out with a naive approach. We can just write an LP and solve this. Okay. So for each allocation, I'm going to have a variable, and the price is going to be a variable for each of the buyer types in the distribution. And we want to maximize the expected revenue. And how do I do this? It's fine. And we have different constraints. I don't want to really get into the LP, but this LP exactly solves the revenue maximization problem. We'll just stick to constant support marginals for now in this example. So even with support size 2 or 3 for each marginal, this is already exponential in n, because the number of variables is going to be exponential in n. So you have 3 to the n many different items, buyer types. And can we do something better? Can we get a polynomial time mechanism, a mechanism in polynomial time? The answer is no, unfortunately. This was shown by Shen et al. In 2015, that for unit demand bias, even with support size 3, you can't find the optimal mechanism in polynomial time unless the polynomial hierarchy collapses. But we also have some good news, which is backed by Paul Milgram because he likes approximations. Finding a mechanism that gets 1/4 approximations to the optimal revenue is polytime solvable. But is this really good news? Because they're already joking about the fact that he doesn't really support this. Who wants to sell things that are that cost $1,000 to $250? Would you do that? Of course, can you do better? And till now, we actually didn't even know a 1/4 plus epsilon approximation. Nothing better than a 4th approximation was known till now for unit demand. And we answer this affirmatively. Yes, we can do better. Our main result is that for unit demand buyers, we can get a mechanism that gets 1 minus epsilon approximation to the optimal revenue, and we can find this in quasi-polynomial time in n. Okay, for any epsilon greater than 0, I can find a mechanism that gets 99.99% of the revenue in quasi-polynomial time. So the distributions need not be bounded or anything. The distributions can be unbounded. So this is one of the first, this is the first mechanism that runs in sub-exponential time for close to optimal revenue for a very general class of distributions. So, yeah. Yeah, so we don't really read the distributions. We need an oracle access to the distributions that gives you density functions and things like that, but also mainly it's I should be able to calculate the Meyerson price given a cutoff. So if I say that, okay, what is the optimal price to set if I have to set a price from X onwards? And so I need oracle access for that. Because if I consider Meyerson to be a simple mechanism, I'm just going to be using that as a oracle access. Yeah. Okay?
By the way, the problem is still difficult even if the distributions were bounded or supported on spree, right? It's still also interesting. It's not clear how to do that.
The distribution is bounded? Yeah, yes, yeah.
If the distribution was bounded, the problem wouldn't be much.
Yes, yeah, I'll come to that. Yeah. But we solve this for unbounded things, but even for bounded distributions, we don't know much. That's a spoiler, but yeah. Yes, so let's see how we got there and what are the challenges we face. I'm going to be talking about this in 3 parts. I won't be really giving any proofs or anything. I just want to tell you why we did what we did and why it was important. So the first step is to show a reduction. We show a reduction from unbounded distributions to bounded distributions, but with an asterisk. I'll explain more about why that is. Okay. So the challenge in this step is that we can't just ignore high-valued buyers if we want close to optimal. Why is that? Let me give you some intuition. Consider just n IID items. So with very high probability, each item has value uniform in 0, 1. And with probability just 1 over n square, it takes a very high value. Okay? So now if I just focus on the core, if I focus on the bounded interval part, I can get revenue 1 by setting price close to 1 because the expected max of n uniform things is going to be close to 1. Okay? But if I focus on the tail, because they have very high values, I can just set price h, and with probability 1 over n, at least one of them is going to be takes value h. With probability at most 1 over n, one thing is going to be at least h, so the revenue is going to be h over n. When these two revenues are like comparable, I can't get better than a constant approximation if I focus only on one of them, right? Because I'm missing out like an equal amount of revenue from the other part. So, but doing both is tricky, and how do we do that? That is the question. And this is where our asterisk comes in. So we focus on almost bounded distributions. By that I mean that they have a bounded interval support except for one high value, which is exactly the example that I gave. Okay? So because of this, we show that we can get a polytime reduction from getting 1 minus epsilon approximations for unbounded distributions to an additive like epsilon approximation for almost bounded distributions. This is one of our key steps. It's kind of involved to proof, but like, so I won't get into the proof. But this is really important, and this has been like, something like this has been done before by Babayev et al. They showed for like additive bidders that they get an almost reduction to a truly bounded distribution. And we extend this in like multiple ways. One, we do some like quantitative improvements, which, yeah, let's not get into that. But more importantly, we give a true black box reduction. So we give a black box reduction, but to almost bounded distributions. And one thing to note is that like, since this is for like subadditive buyers also, like we hope like people can use this to like prove things in the future for beyond unit demand, and I'm currently working on the additive case as well. So yeah, so all we now need to focus is on almost bounded distributions. We don't have to worry on unbounded distributions at all. Just solve that independently of everything else. Yeah, so the main thing to take away from that part is that we have a polytime reduction from unbounded distributions to almost bounded distributions. But we can't ignore high-valued buyers, but I can capture them with one single number. I can, even if it's a fat tail, I'll give you like one like very big number to capture the tail.
But then you can find the bound, right? Take the maximum.
Yeah, but like it can be like, okay. It's because of some scaling things. The bounded part needs to be like much smaller than the, yeah, so there is like a slight like technicality there. Yeah. Okay. Does anybody have any questions in the first part of this proof? Cool. Okay, now that we got to bounded, almost bounded distributions, as like Noam said, even this is like tricky. Why do I have to go to something called symmetric distributions, and like what is even that? Like why can't I just solve for like bounded distributions? Take this like very simple example of n product distributions that just take 2 values each. So item I takes value 2 with probability 1 over I and 1 otherwise. So there are 2 to the n many different types of buyers in this case. This is a bounded distribution. And the LP that I showed you before like is going to have exponential many variables again, and this is going to take exponential time. So can we do better than this? Can we have like a p-task for bounded distributions or something like that? We don't know. Even now, we don't really know what is the answer, whether there is a p-task or there is no p-task for bounded distributions. Okay. So what we knew before was that for these special kinds of distributions called symmetric distributions, don't worry about the text right now, we could find optimal mechanisms in polynomial time. So we did not know about bounded distributions before, but we had this very nice result by Daskalakis and Weinberg that gave an optimal mechanism in polynomial time for these specific kinds of symmetric distributions. What do I mean by symmetric distributions? Take this like very toy example. Okay, that's supposed to be a soccer ball. I don't know whether you can see it. So the buyer's value, let's say this buyer has value 5 for a soccer ball and value 8 for basketball. And consider a different buyer like who has swapped values. She has value 8 for the soccer ball and value 5 for the basketball. And if the probability of seeing these two types of buyers is the same, and if it's same for any values x and y, we say that this distribution is symmetric with respect to swapping the basketball and the soccer ball. Okay? So more like specifically, we say that the distribution is symmetric with respect to a permutation sigma if the density of, for any type, if the density is the same as the density of the permuted types for that sigma. Okay? This is true for any types. And so why is this interesting? It's because this reduces the problem size a lot. The LP, we can write the LP differently such that it has much fewer variables by grouping together like equivalent types and like treating them similarly. For example, let's say that like we have n identical items. So this is like very highly symmetric. There are still 2 to the n many different types of buyers. But all we need to know is like how many items are valued at 1 and 2. So we can like count them differently. We can say that, oh, there's a representative RK for all the types of buyers with exactly k balls in bin 1. So if the buyer has k items with value 1, we treat all of them the same. So the number of variables that we need in this modified LP is going to be just order n. And so we have like a polytime algorithm for this instead of the exponential LP. Yeah, so now getting back to their result. So they say that if you can group together the items into S groups where each marginal is of support at most C, within each group, all the items are IID, then we can find an optimal mechanism in n to the CS. So this is just about counting representatives that are needed for like distinct, instead of distinct representatives that are needed to like cover all the types. Like it's just like a balls and bins calculation. So because in each group, you can have at most n items that take a particular value x. So there are n to the, so in this case, there can be n to the 4 many different partitions of this. And similarly, there are going to be s different groups. So it's going to be n to the CS. Okay? Ooh, how much time do I have left? Oh my God, okay. So, okay, let me like go do this quickly. So all we need to know is that the marginals have small support and there are going to be like there are only few distinct marginals. Yeah, so symmetries are awesome even though the boundary distributions are still a mistake. So how do I symmetrize this? Okay. So we give a transformation from any like almost bounded unit demand distribution to an almost bounded symmetric distribution with small support and few distinct number of marginals. Here, like this transformation needs to be done carefully because just because some distributions are close does not mean that the revenue is going to be preserved. For example, here, like the optimal mechanism here will give 50 revenue for D1, but like it's 0 for D2 if you set price 100. So we transform this into a closed symmetric distribution and find the optimal mechanism now because we have the Daskalakis-Weinberg result. And then we also transform the mechanisms so that we preserve revenue. Like I have to transform that carefully and transform this carefully to make sure that I get almost optimal revenue. So the takeaway here is that even though symmetric distributions are great, they are very fragile. So I can't just say that, oh, I can optimally solve for symmetric, so I can almost optimally solve for almost symmetric very easily. Like that needs to be done carefully. Okay, so coming back to the main result. So we get an epsilon, 1 minus epsilon approximation to the optimal revenue, and we can find this in quasi-polynomial time. The key steps are reducing unbounded distributions to almost bounded distributions and symmetrizing almost bounded distributions. Okay? Now let me change gears in 2 minutes and talk about a different lens of using menu complexity. So we know that a menu is a collection of all possible distinct outcomes of a mechanism. This is one possible menu. It can also have randomized lotteries. So a menu is equivalent to a truthful mechanism, and menu complexity is just a number of distinct outcomes. So in a symmetric menu complexity, I'm going to make a more compact menu, but with an implicit contract already. So here you have 7 different options, but I can just give you a different menu that says that, oh, if you want one ball, pay $6. If you want 2 different balls, pay 10, and if you want 3 different balls, pay 14. And the asterisk just says that you can take any combination of the balls. It can, I don't have to specifically tell you what they are. These 2 menus are equivalent. So in a symmetric menu, I'm going to say that, okay, if I give you a allocation and pair, I'm also implicitly giving you the permutations of the allocations and the pairs. This is a generalization of menu complexity. A trivial case would be to just say that this group is the trivial group, so then the symmetric menu complexity and the menu complexity will be the same. Otherwise, we can get a more compact menu, but implicitly offering all the permutations, relevant permutations. Okay. So the second part, our second main result was that for the same mechanism, it only has quasi-polynomial symmetric menu complexity if you want to get almost optimal revenue. Yes, and we had other cool results that you can ask me about later. So to summarize, so we give a sub-exponential upper bound that gets almost optimal for a general class of distributions, specifically unit demand. It's a true reduction from unbounded distributions to almost bounded distributions, and this is for subadditive Bayes. So this is a black box reduction, and we only have to worry about almost bounded distributions from now onwards. And we exploit symmetries even in seemingly asymmetric distributions. And we define this new notion of symmetric menu complexity and have interesting results for that. Yeah, and this is some future work. Thank you.
Can you go back to the slide that you skipped over with the other results for additive and stuff like that?
Oh, sorry.
Oh, that's IAD.
Oh yeah, this is additive IID.
Yeah.
Sorry, yeah.
Any questions?
Okay.
One small question.
Yeah.
Do you need to work with full symmetry in the distribution, or can you also use, if you have smaller symmetry, for just part of the permutations? Can you do anything with it?
Oh yeah. So we don't need full sorry. Let me go back to. Yeah. So it's So smaller symmetries will give you bigger.
In the previous part.
So what do you mean by smaller symmetries?
If you don't have a symmetry for all the permutations, just have some.
Yeah. So what we need is that it needs to be, let's say, a permutation group. It need not be the full permutation group. So if I have a subgroup, sigma, and then I can, so basically the asterisk is going to come with the subgroup. I'm going to tell the buyer that look at this menu, you can permutate with any permutation in this subgroup, and I can describe the subgroup in polynomial time. So yeah, so it need not be the full group. I will give a different subgroup. Yeah. Okay. Thank you.